There's one more important result I want to prove before we're done with this section. But before we jump right into it, I want to prove there's a couple lemmas we need to prove that will help us in proving the main theorem. Recall that a lemma is just a kind of a little theorem that you prove before the main result, kind of like a helper theorem. Okay? For this one, if a linearly independent subset of Rn contains m vectors, then m must be less than or equal to n. All right, so let's go ahead and start our proof. Our assumption is that we have a linearly independent subset of Rn with m vectors. Okay, so let's let v1, v2, all the way to vm be vectors in Rn, and let's let this set be linearly independent. All right. Now, what does it mean to be linearly independent? Well, the main definition we keep on going back to is that a linear combination of these, the homogeneous equation of these. So if I take a linear combination and set it equal to 0, okay, this is the homogeneous equation. This has only the trivial solution. Where all the coefficients would be equal to 0. Okay? What I want to do is I want to take this, I want to think about the coefficient matrix. Okay? We've learned that a linear combination equation like this, we can solve it by taking the coefficient matrix, the augmented matrix, and getting it into reduced row echelon form. Okay? Actually, instead of observe, let's say consider. So we're going to take the matrix. The coefficient matrix is made up of the vectors v1 to vm. Those are the columns of the coefficient matrix. Okay. And normally, the augmented part would be what's on the other side of the equation, right? All zeros. But when it's all zeros, we usually leave it off. Notice the size of this matrix. We clearly have m columns, right? Because we have m vectors. But how many rows do we have? Well, v1, all these vectors, v1, v2, vm, they're in Rn. They're n-dimensional vectors. So this is a matrix with n rows and m columns. So let's consider this n by m matrix, and let's call it A. All right? What would be the rank of A? Well, if this system has only the trivial solution, then if we get this thing in reduced row echelon form, we would need to have no free variables, right? Otherwise, we'd have infinitely many solutions. So in reduced row echelon form, we can't have any free variables, which means every column must have a leading entry in it. Observe, because let me just take out observe actually. Because the vectors v1 to vm are linearly independent, the rank of A must be equal to M. Otherwise, we would have free variables. And the homogeneous system would have an infinite number of solutions. And let me just explain that a little more, because sometimes it can be a little hard to follow when we're dealing with an abstract matrix. So this is the homogeneous system written in linear combination form. But in matrix form, our coefficient matrix are the columns V. And then we multiply by our coefficients A, the vector of coefficients A, and that's going to be equal to the 0 vector. Okay? This equation and this equation are the exact same thing. They're just written in two different ways. One's written as a linear combination equation, the other's written as a matrix equation. Okay? But they're saying exactly the same thing. All right? To solve a system like this, remember, we would take the coefficient matrix, augment it with what's on the other side of the equation, get in reduced row echelon form. Since the other side is just 0, we usually leave that off. We don't augment with 0, but that would be this matrix here, right? That's matrix A, the coefficient matrix. Okay? So the rank of this matrix determines the number of solutions to our homogeneous equation. But because these vectors, v1 to v2, vm, these are linearly independent, we have only the trivial solution here. A1, A2, AM, they must all be 0. And so the rank of this matrix must be equal to M. Every column has to have a leading one, because if there's a column without a leading entry, then that means that the variable corresponding to that column would be a free variable. And if we have a free variable, we have infinitely many solutions. And we just said we only have one solution, the trivial solution. Okay? So that's the argument we're putting forth. All right? So the rank must be M. But the rank of A has to be less than or equal to the minimum of the number of rows and the number of columns. Okay? Because remember, the rank, one definition of the rank, the definition that I prefer to think about, is that the rank is the number of leading terms in the matrix when in reduced row echelon form, or in row echelon form. Okay, it's the number of leading entries of a matrix in row echelon form. Each leading entry has to be in its own row and its own column from all the other leading entries. So the rank has to be smaller than the number of rows and the number of columns, or no larger than. It has to be less than or equal to the number of rows and the number of columns. So we just said the rank is equal to M. Okay? And the rank has to be no larger than the smaller of the number of rows and the number of columns. If it's equal to the number of columns, then it cannot be, then the number of columns cannot be larger than the number of rows. Since the rank of A is equal to M, it follows that M is less than or equal to n. Okay. Let me explain that a little more thoroughly with concrete numbers. Okay, say m is 5. Okay, we know that the rank of A is equal to 5. Now say n is smaller than 5. Say n was 3. Okay, we know from here that the rank of A is equal to 5 because 5 is the number of rows, right? But this inequality says the rank of A can't be any larger than the minimum value of these two, which if n is the smaller value would mean that this would be 3, and the rank couldn't be larger than 3, which would mean we'd have a contradiction, right? You cannot have n smaller than m and satisfy this condition here. Okay, so m cannot be larger than n. Our number of columns cannot be larger than our number of rows, and that proves the theorem. That proves the lemma. All right, so lemma 1 done. And it makes sense if you think about it. If you have a subspace of Rn, then the basis for that subspace should have fewer vectors than Rn. The dimension of the subspace should be smaller. Okay. All right. And let's consider another lemma. Okay. Again, this lemma is going to help us prove the big theorem we have. All right. So let's let v1 to vk be a linearly independent subset of Rn. And then we take another vector u that is not in the span of v1 to vk. Okay, so it's not already in the span. Then if we add on the u to v1 to vk, that new set with the extra vector is also linearly independent. All right. Okay, so what we're going to do, we want to show this is linearly independent. Okay, the usual way to do that is look at a linear combination of the vectors, look at the homogeneous equation, show that the coefficients must be 0. So I take some scalar times u plus some scalar times v1 plus some scalar times vk, and then we set it equal to 0. So we're looking at the homogeneous equation. In order to show these are linearly independent, we need to show this equation has only the trivial solution. That is, the coefficients a and a1 and ak, they have to be 0, and that's the only way to do it. Okay, so again, we're going to prove this by contradiction. We're going to assume that a is not 0, and we're going to show that that's nonsense. If a is not 0, then I could solve for vector u. I could subtract a1 v1, I could subtract ak vk to the other side, all the other v's to the other side, and then I can divide by a. Okay? So u would be negative a1 over a v1 plus all those other v's plus negative ak over a vk. Okay? Notice we did need, this only works if a is not 0, right? Because you can't divide by 0. If a is not 0, we can do this. We could solve for u, and as part of that solution, divide by a. But this contradicts the assumption that u is not in the span of v1 to vk, right? One of the conditions of being in the span, well, yeah, the condition of being in the span is that we would be able to express the vector as a linear combination of the v's, and that's exactly what we've done here, right? We have expressed u as a linear combination of the v's, constant times a vector plus a constant times a vector, which means u would be in the span of the v's, and that contradicts the assumption. That's the nonsense part. Okay, so we got to that nonsense by assuming a wasn't 0, the coefficient of u wasn't 0. So since we can't, since that's nonsense, it must be that a actually is 0. Okay? But if a is 0, this is gone, right? That's just 0. And so then we just have this equation. And that's just, we already know that the v's are linearly independent. And since this is a homogeneous equation, all the coefficients in front of these must also be 0. Okay, A, 1 to A, K must all be 0 because the V's are linearly independent. So that means that this equation has only the trivial solution. We've shown that all these coefficients have to be 0, which means that this set of vectors is linearly independent. Okay? So if we add a vector that's not already in the span of the vectors to that spanning set, then the new set is still linearly independent. All right? And with those two out of the way, we're ready for our big result for this section. Okay? Theorem 7. So let's let V be a subspace of Rn. Any linearly independent subset of V can be expanded to a basis of V. Understand what this is saying. This says that every vector space that is a subspace of Rn, every vector space has a basis. We can find a basis, a minimal spanning set for every subspace, a spanning set that is linearly independent for every single subspace. Okay? Always, you can always find it. It exists always. Okay? So what we do is we start with a linearly independent subset of the subspace V. We know we can find it because V is non-empty. One of the conditions of being a subspace is that it's not empty. So V has at least one vector in it. So at the very least, you could just pick one vector for this set. Okay? And we know one vector all by itself is linearly independent, of course. Right? So pick any linearly independent subset of V. We know we could find one. If the span of that linearly independent subset is the vector space, then hey, guess what? We have a basis because it spans a set and it's linearly independent. And we're done. Okay? That's the boring case. So instead, suppose that the set of vectors we pick, they don't span vector space V. Which means there are vectors that are in V that are not in the span of X. So choose one of them. Choose a vector that's in the vector space V so that the vector is not in the span of my original choice of vectors. Okay? And now add that to the set of vectors. So I have my original set of vectors. Throw in U1. Throw in that vector I just chose that wasn't in the spanning set. We just proved a lemma about this, lemma 6. If I have a set of linearly independent vectors and I pick a vector that's not already in the span, then add that vector to the original set, that new set is linearly independent. Okay, so now we're using the lemma. We're using lemma 6. So we have a new set of vectors that is still linearly independent, right? And is still a subset of V. And then we kind of repeat the process. If the span is equal to V, hey, we're done, great. Otherwise, choose another vector that's in V so that it's not in our new larger linearly independent set of vectors, not in the span of that new larger linearly independent set of vectors. Again, we know it exists if the span's not equal to V. That means there's something in V that's not in the span. Okay, so pick one of those things. Doesn't matter which one. Again, we could add that to our existing set. That just makes our set larger. Now we have an even larger linearly independent set of vectors that live in V. And the process continues. Okay, we could keep doing this until this condition is met, until the span of the vectors is equal to V. We claim that a basis will be reached eventually. How do we know? How do we know we won't just go on adding vectors forever? Okay. Because of lemma 5. Lemma 5 says if we have a linearly independent subset, then that subset must be less than or equal to n in Rn. Okay, so remember, vector space V is a subspace of Rn. So we could keep on adding vectors, but we can't do it forever, because at most, the most vectors we could have in a linearly independent subset would be n. We cannot be larger than that. Okay? And so since we can't continue the process forever, at some point the span must be equal to V. All right? Otherwise, we'd just be able to continue the process forever. And so that proves the theorem. It means that we could take any linearly independent set, and this describes how we could expand that into a basis for V. But it also means that every vector space, that is every subspace of Rn, okay, has a basis. Every subspace. This means any subspace V of Rn can be is a span of vectors. Okay, so spans are really important because every subspace can be written as a span of vectors. If we can find a basis, then that basis spans the vector space, which means every subspace of V can be written as a span of vectors, and every subspace V of Rn has a basis.